Hello everyone, welcome to the presentation of our paper about the estimation of frequency response using a data-driven method. My name is Bruno Pinheiro and I am a master degree student at the University of Campinas. With the several transformations that the model power system has been undergoing, the system's operation and dynamic are drastically affected. The reduced inertia of solar and wind power plants results in a higher rate of change of frequency, endangering the power system frequency stability. In addition, with the enhancement of monitoring system, an amount of data are collected by which our measurement system that can be used for different data-driven methods for power system parameter estimations. In this context, the main objective is to estimate the key parameters that drive the frequency response of asynchronous generators, using PMU measurements after disturbance. Based on this measurement data and an underlying frequency response model, the generator's inertia and damping and the turbine governor parameters can be properly estimated using a system identification approach. Firstly, a mathematical model based on the well-known single equation are considered. Using the common consideration that soon after the disturbance occurs, the mechanical power variation can be neglected, a first-order transfer function is obtained to describe the frequency response of the generator. However, when the turbine governor system is considered, a second-order transfer function is used to describe the dynamic frequency response. With the two reference models, a system identification is employed. It should be noted that the PMU is assumed to be installed at the generator connection bus, with the measurement of frequency and active power. Using this dataset, the procedure is divided into three steps: preprocessing, system identification using Armax models, and finally parameter estimation. The preprocessing step consists basically of the resample and filter the collected signals. Then, a discrete time Armax model with orders 1 or 2 is estimated, and your deterministic part is converted to continuous time domain. Finally, in the parameter estimation step, depending on the order of the estimated model, the parameters of the frequency response can be directly extracted from the comparison with the reference models. This proposed methodology is applied in a reduced power system with 2 generators, 5 buses, and 1 load, when only generator 1 is equipped with turbine governor system. In the first analysis, we are interested in determining the parameters that can be accurately estimated using a first-order Armax model, and evaluate the influence of the data window size. For generator 1, the relative error for inertia and damping coefficient is presented jointly with the mechanical power deviation. It is clearly observed that the relative error increases over the time for both parameters. Before the turbine governor actuation, the minimum relative error obtained for inertia is less than 2%, and for the damping coefficient is around 8%. Therefore, this effect is even worse for the estimation of the damping coefficient. For the generator 2, as expected, without the turbine governor actuation, both parameter estimation converge to the true value when the window size increases. And it is interesting to note that the relative error for inertia are lower than the damping coefficient. Furthermore, the convergence speed is also higher for inertia than for the damping. Now, in order to estimate the parameters of the turbine governor system and improve the generator's parameter estimation, a second-order Armax model is employed. The result shows the relative error for inertia and the damping estimation for generator 1, as well as the estimation of the droop gain and the time constant of the turbine. In this case, the second-order Armax model is capable to identify all parameters with relative error less than 5%. And the advantage to use the second-order Armax model when compared to the first order is to eliminate the necessity to clearly identify the instance of the primary frequency control actuation. And the results show that the frequency response parameters, inertia, damping coefficient, droop gain, and time constant of regulator can be estimated using the second-order Armax model with relative errors below 5%. On the other hand, the first-order Armax model has its application reduced to inertia estimation in a specific data window. For the future works, the turbine governor system can be improved and the methods applied in a large-scale power system. More details can be found in the paper. Thanks for watching.